Welcome to your first official lesson of the new semester. We're going to talk about probability of compound events. So let's get started. So firstly, a compound event basically means the combination of two or more simple events. So that could be, we're finding the probability that this happens and this happens, or it could mean that finding the probability this happens or this happens. So when we're kind of compounding those two events. So first we're going to talk about the idea of independent versus dependent, because that's going to make a difference in some of our probabilities. So some of this I'm going to skip through a little quicker, just so you know. So if two events A and B are independent, and that means that probability of B does not affect the probability of A. So that's when two events don't affect each other. Dependent would mean when the two events do affect each other. There's a lot of different reasons that either of those things could happen. I'm going to skip through some of this notation stuff because I'm not as worried about it. And events that occur without replacement are usually dependent. We'll get into some examples with that scenario in a little bit. So example one, we're going to talk about whether the following sets of events are independent or dependent. So if we were to roll a fair six-sided die and then draw a card from a deck of cards, do those two events or do those two things affect each other? And in this case, they really don't. If I roll a 6 on a die, that's not going to make it more likely for me to draw like a queen from the deck of cards. They don't really affect each other at all, so those would be independent. If I were to draw a marble from a jar, and then without replacing that first marble, draw a second marble. Well, the second time I pick, there's less marbles in the jar, and there's less of that particular color. So that probability of getting a specific color of marble on my second pick has now changed a little bit. So those would be dependent if I'm not putting that marble back. And that's what we meant by without replacement. Part C, rolling a fair six-sided die and then rolling it again. Well, when I roll a dice, it's not like if I roll a 6, the 6 disappears and I can no longer roll a 6 again. All the sides are still there. So every time I roll that dice, I have the same chance of getting any side. So that would be independent. Drawing from a deck of cards and then drawing a second card. So if I draw a queen, it's a queen of spades. There's now one less queen in the deck. There's one less card in the deck. So my probability of getting a queen on that second pick, my second card, has now changed a little bit. So those would be dependent. And then lastly, we have drawing a marble from a jar, replacing it, and then drawing a second marble. Well, now, since I've replaced the first marble, my probabilities stay the same. I have the same number of marbles each time. I have the same number of each color of marbles each time. So nothing changes. My probabilities would be independent. So our AND rule is describing or explaining how we find the probability of this and this. So the probability that two or more events occur is found by finding the product, so that means multiply, of the individual events occurring as long as the two events are independent. And we'll talk another day about what happens if they're dependent. We actually talk a little bit about that today too. So if A and B are independent, then the probability of A and B can be found by just multiplying probability of A times probability of B. So let's look at some examples of that. Suppose we roll a fair six-sided die and then flip a coin. So firstly, are these events independent or dependent? These would be independent because the outcome of the die roll is not going to affect the probability of flipping a heads on the coin. So they're independent. So part B, what's the probability of rolling an odd number on the die and flipping heads on the coin? So we want probability of odd and heads. Our rule that we just learned says, as long as they're independent, which they are, I can just multiply probability of odd times probability of heads. So probability of getting an odd on a die, there are 3 sides on a die that have an odd number, 1, 3, and 5, out of 6 sides total. So 3 out of 6, times probability of getting heads on a coin, there's 1 heads out of 2 sides total, so 1 out of 2. With fractions, we multiply the top, multiply the bottom, so 3 out of 12, which reduces to 1/4, or you would usually just put it as a decimal, so 0.25. Another example, suppose a game has a spinner in which purple takes up 50% of the circle, and we decide to spin the spinner 6 times. So firstly, are the events independent? So in other words, when I spin the spinner multiple times, is the second spin going to be affected by the first spin? And the answer is no. These are independent because it's It's not like when I spin purple on the first one, there's like less purple on the circle. Like the circle stays the same. So it would be independent each time I spin the spinner. So the probability of spinning purple 6 times in a row would be like saying, what's the probability of getting purple and purple and purple and purple and purple and purple again? It's a lot of purples. So I'm going to multiply. Same as I did before, because these are independent events and I want a lot of ands to happen. So probability of getting purple, according to this up here, is 50% or 1/2. So I'm going to do 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2. You could also just do in your calculator 0.5 times 0.5 times 0.5 times 0.5 times 0.5 times 0.5, and that would work as well. But if I use the fraction, multiply all those, I get 1/64th, which is about 0.01565. So those are 2 examples of using our multiplication rule in probabilities. Now we're going to look at a different type of example. We have here what we call a two-way table. Ms. Sorensen surveys her class about whether they like cats and dogs. The results are shown here. I can see the number of people who like both cats and dogs, who like dogs but not cats, etc. You'll notice that this table does not give us the total, so if that ever happens, great first step is to go ahead and total up each column and each row. So I'm going to do that real quick. And now we'll move on to our examples. The totals just really help when we are finding probabilities. So part A, what's the probability that a student likes dogs? So probability that someone likes dogs, my basic probability, I'm going to do the number of people who like dogs, which is 20. 20 people total like dogs, out of the total number of students in the class, which is 25. So 20 out of 25, which is 0.8. Part B, what's the probability that a student likes cats? So same idea, probability of likes cats. We want the number of people who like cats, which total is 16 out of 25 total. 16 out of 25 is 0.64. So then part C says, what's the probability that a student likes cats and dogs? So if I was using my rule that we just learned, then you might think I should just multiply 0.8 times 0.64. But remember, that only works if those 2 events are independent. And really, in this case, we don't really know for sure, but they're probably not. Right? If someone likes dogs, they're probably more likely to like cats than just the average person. If you like one type of animal, you're more likely to like a different type of animal. Animal lovers unite. So these are likely not independent situations, and in any case, I'm not sure. So instead of trying to use that rule to multiply, I'm just going to use the table. So I can see in the table the number of people who like both cats and dogs. So I'm just going to use that. So my probability that someone likes cats and dogs, there are 15 people in our table who liked both out of 25 people total. And that's how I'm going to deal with that problem. So 15 out of 25, which is 0.6. So when I have a two-way table, the easiest way to deal with any probabilities is to just use the table. Suppose I pick 2 students randomly from the class without replacement. What's the probability that both students like dogs? So I can get the individual 1% probabilities from the table, but as soon as I'm talking about multiple students, now is where I'm going to have to start applying those AND rules that we talked about a little bit ago, the multiplication rule. So probability that both students like dogs. So dogs and dogs. So when I pick my first student, probability that that first student likes dogs would be 20 out of 25, right? There's 20 who like dogs out of 25 total. But if I'm doing this without replacement, that basically means I don't want to pick the same student twice. I'm dealing with 2 different students here. So when I go to pick that second student, I've already picked 1 student who likes dogs. So now there are only going to be 19 students who like dogs, and there are only going to be 24 students total. So I have to make a slight adjustment. This is another example of a dependent probability, but I can still use that multiplication rule because I'm changing or accounting for that slight change in probability. Do a little multiplication, still multiply the top, multiply the bottom. 20 times 19 is 380, 25 times 24 is 600. So it would be 380 out of 600. It reduces down to 19 out of 30. But either way, when I divide top by bottom, I'm going to get 0.6333. pretty much always going to have answers as decimals anyway, so don't worry too much about the fractions. Part E, what's the probability that neither student likes dogs? So not doesn't like dogs and doesn't like dogs. So same idea, just different numbers. First time I pick a student, there are 5 who don't like dogs out of 25 total. And then the second time I pick a student, there are now only 4 who don't like dogs out of 24 total. So again, 5 times 4, 25 times 24 would be 20 out of 600, which reduces to 130. When we divide that, we get 0.0333. But if we just divided 20 by 600, we would still get the 0.0333. What's the probability that the first student likes dogs and the second doesn't? So same idea, but now we're kind of mixing it up a little bit. So likes dogs and doesn't. So the first time I pick a student, 20 like dogs out of 25 total. The second time I pick a student, this time we want doesn't like dogs. So we have 5 of those left. That hasn't changed. But as a total, we only have 24 students to choose from because we already picked one. So it would be 5 out of 24. Again, multiply top, multiply the bottom. That would give me 100 out of 600, which reduces to 1/6, so 0.1667. And then lastly, we have probability that the first student doesn't like dogs and the second does. Same thing, opposite order. So first time I pick a student, 5 don't like dogs out of 25 total. Second time I pick someone, there are 20 who like dogs, but we're only going to have out of 24 students total. But that does come out to the exact same answer as the last part, which is interesting. So all of that we dealt with before was dealing with the and rule and dealing with independent versus dependent events. So now we're going to move on to a different vocabulary term that's important with probability, which is mutually exclusive. So if 2 events, A and B, are mutually exclusive, another word you might see used for that is the word disjoint. That means that A and B cannot both happen. So mutually exclusive basically means there's no overlap. If you think about like a Venn diagram, and where they overlap is where they're both. So if 2 events are mutually exclusive, there's no overlap. It can't be both. It has to be one or the other. So in this example 5, we're going to look at a few sets of events and decide whether or not they are mutually exclusive. So part A, if we flip heads on a coin and then flipping tails on the next flip of the coin. So the question is, can both of those things happen? And the answer is yes. Because we're dealing with 2 separate flips of the coin, it is very possible to flip heads first and then on the next flip to flip tails. So both of those things can happen. So that would be not mutually exclusive. Part B, having blue eyes and being over 6 feet tall. So again, the question is, can you be both? Can someone have blue eyes and be over 6 feet tall? Well, sure. I mean, I don't know anybody personally, but I'm sure that they exist. So because both of those things can happen, that would not be mutually exclusive. Think of mutually exclusive means that they are both excluding each other. So they can't both happen. And that's not the case here. Part C, flipping heads on a coin, and then flipping tails on the same coin flip. So the same coin flip. Can I get heads and tails on the same coin flip? No, that's not possible. There's no overlap there. It's going to be heads or tails. It can't be both. So that would be mutually exclusive. And then lastly, being over 6 feet tall and being under 5 feet tall. Can a person be both taller than 6 feet and shorter than 5 feet? No, they can't. It's got to be one or the other or neither, but it can't be both. So that would be an example of mutually exclusive. So when they can both happen, it's not mutually exclusive. If they can't both happen, it is mutually exclusive. It was a little backwards, but that's what it is. So where this goes to is what we call the OR rule. The OR rule tells us what to do if we wanted to find the probability of something or something else. And there's 2 different ways we have to deal with this depending on, are they mutually exclusive? Is there overlap with these 2 events? So if A and B are mutually exclusive, then the way we find the probability of A or B is to simply add the 2 probabilities. So the basic OR rule is we add. But if they're not mutually exclusive, meaning that there's some overlap, those 2 things can sometimes happen simultaneously, then we have to account for that overlap. So the way we find that OR probability is by doing probability of A plus probability of B minus the probability of A and B, which is that overlap. And you'll see why we have to do that when we get to an example. So we'll start with a basic example. A jar has 4 marbles in it, 2 red, 1 white, and 1 green. You want to find the probability of getting a red or a white marble when you're picking one marble from the jar. So is the situation mutually exclusive? And the answer is yes, right? A single marble cannot be both red and white. It has to be one or the other. So they are mutually exclusive. There's no overlap. And when they're mutually exclusive, that makes my OR probability a little easier because I know I can really just add the 2 probabilities. So if I want probability of a red or white marble, I'm going to do probability of red marble plus probability of white marble. So probability of red marble, there are 2 red out of 4 marbles total, plus probability of white marble, there is 1 white out of 4 total. So 2/4 plus 1/4, which is 3/4 of 0.75, right? It's a little simpler when they're mutually exclusive because we don't have to worry about both. So now let's go back to that cats and dogs survey, very important survey. Suppose we wanted to find the probability that a randomly chosen student from Ms. Sorensen's class likes cats or dogs. So firstly, is this mutually exclusive? So in other words, can someone in Ms. Sorensen's class like both cats and dogs? And the answer is yes. Not only do we know that in our heads, we also see that in the table. There are 15 people who like both. There is overlap. So this is not mutually exclusive because a student can like both. And because they are not mutually exclusive, that makes our OR probability just a tad bit trickier. So, probability that they like cats or dogs, our basic rule is we add, right? Probability that someone likes cats, 16 people like cats out of 25 people total, plus probability that someone likes dogs, 20 people like dogs out of 25 total. But if I just stop there, if I leave it at this, firstly, I'm going to get 36 out of 25, which doesn't make sense numerically. But what's happened is these 15 people who like both cats and dogs, 15 is part of the 16 and 15 is also part of the 20. So if I leave it here, those 15 people are being counted twice. And we don't want to count anything twice. We don't want to overlap and double count part of our answer. That doesn't make sense. So that is why we have to subtract that overlap or subtract that and piece. So I'm subtracting the people who like both so that they're only being counted once. So 16 plus 20 minus 15 gives me 21 out of 25, which works out to 0.84. So let's do one last example where we just kind of put everything together that I've talked about in this lesson, the and the or. So a random sample was taken of McNeil High School graduates who had completed both geometry and algebra 2 in some form or another while in high school. We've got our table. I'm going to go ahead and find all of the totals. So we have those to use to find our probabilities. So suppose we choose a student at random. Part A, what is the probability that that student took advanced geometry? The total, we have 221 people out of 656 who took advanced geometry. So 221 out of 656 is 0.337. B, what's the probability that they took advanced algebra 2? Total, I have 180 who took advanced algebra 2 out of 656 total. Comes out to 0.274. Now let's get into some of those compound probabilities. Next part, what is the probability that they took advanced geometry and advanced algebra 2? I want to be careful. I'm not going to multiply because I'm really just talking about one student and I know I can just look at the table. So if I look at the table, I see that there are 157 students who took both advanced geometry and advanced algebra 2. So 157 out of 656, which is 0.239. Okay, now as a side note, where I might use the and or the multiply in this situation is if they were asking, suppose we chose 2 students at random, what's the probability that they both took advanced geometry? That's where I might have to do some multiplication. So like 221 out of 656 times 221 out of 656. whatever. So you get what I'm saying. So we multiply if we were talking about 2 students. So then the last part, what's the probability that the student took advanced geometry or advanced algebra 2? So our OR rule, right, our basic OR rule is that we add. So probability of advanced geometry was 221 out of 656. Probability of advanced algebra 2 is 180 out of 656. But if I just stop there, those people, those 157 who took both, are part of both totals, so they're being counted twice. So I have to subtract the 157 out of 656 to make sure that there's no overlap, that we don't count anybody twice. That leaves me with 244 out of 656, which is 0.372. So that is our lesson about compound probabilities. We will talk more about this in class next time. Have a good rest of your day.